So yesterday we talked about limits of sequences. So informally, a sequence is just an ordered list of real numbers. Or technically, it's a function where the domain is this discrete set, like the natural numbers. And if we list those numbers, they go on forever. The question is, well, do those numbers, does that list approach something as n goes up to infinity? And that's what we talked about yesterday. All right, so as far as strategy goes, we can sometimes try to pass to a continuous variable. The thinking is, if all the curves on a smooth graph go to a certain y value, then the discrete points on that smooth graph have to go to that same value. We also have things like the squeeze theorem and all the other limit properties. Okay. When we talked about sequences, the name given to the individual numbers were called terms. Technically, terms are things that you add or subtract. And so that's what we're talking about today, is we're talking about series or infinite sums. So here's the kind of thing we're talking about today. This is using that summation notation. I know you reviewed this in Calc 1 when you did your Riemann sums. But this means you just start off A1 plus A2 plus A3 plus A4 plus ... That means and so on up forever. You follow? The question is, how do we define such a thing? So we'll call that sum capital S. What we do is we do what we always do. We're going to start off with something we understand from pre-calculus, a finite sum. This is called the nth partial sum. It's called a partial sum because we're not adding up the whole sequence. We're only adding up the first n terms. You follow or not? Okay. And then what we do is we define S to be the limit as n goes to infinity of S sub n, provided the limit exists. Okay. Provided the limit exists. So there's a couple other different ways to think about what's happening here. First, if we think of S as the sum, k goes from 1 to infinity of a sub k, and S sub n as the sum, k equals 1 to n of a sub k, then the sum, k goes from 1 to infinity of a sub k, is the limit as n goes to infinity of the sum, k goes from 1 to n a sub k. And does this concept look hauntingly familiar to you? Doesn't this look like what we did last week? So remember when we had integrals from a to infinity, f of x dx? It's like, well, what the heck does it mean to integrate to infinity? We just replace the infinite limit with an upper limit and let that upper limit go to infinity. You with me or not? Okay. And the same words apply to these infinite series that apply to integrals. If the limit exists, we say that the series converges. If it doesn't, we say the series diverges. So those words converge and diverge are the same. Tying this idea back to what we did yesterday, if I think about these partial sums, so that's A1, S2 is the sum of the first two terms, S3 is the sum of the first three terms, S4 is the sum of the first four terms, and so on. The limit S is the limit as n goes to infinity of S sub n, i.e., we're looking at the sequence of partial sums. So if we're looking at if a series converges, we're really going to be looking at the end of the day, its sequence of partial sums, which ties it into what we did yesterday. Okay? So there's callbacks conceptually to what we did last week with improper integrals, and there's callbacks to what we did here. Speaking of integrals, I'll do this last thing, then we'll get on with the business of the day. Remember, when you graph a sequence, you're just going to get dots. So here's 1, 2, 3, 4, 5. And you're going to get, a sub 1, a sub 2, maybe a sub 3, a sub 4, etc. You follow? Now, if you look at the sum, k goes from 1 to infinity, a sub k, a sub 1 plus a sub 2 plus a sub 3, and so on. If you want, you could really think of this a sub 1 as a sub 1 times 1, a sub 2 times 1, a sub 3 times 1. And then I could interpret this as an area. What's the distance between each and every one of these natural numbers? It's always what? 1. So if I went in and drew a rectangle here, this rectangle would have height A1, base 1, so it'd have area what? Does that make sense? And I can do the same thing. We'll talk more about this tomorrow or Thursday, probably tomorrow. Okay. In other words, if I really wanted to think about this, I can think of this as a discrete integral. All right? So if I take, in other words, if I take this sequence and I turn it into a piecewise function, I got to be careful with these endpoints. One of these step functions, then the infinite sum really is the area underneath that function, underneath that curve, which corresponds to the infinite sum. Okay? So it's worth having in the back of your mind that these summations are discrete integrals, because we'll see some correspondences between integrals and these sums. You follow? All right. So let's take a look at this example. Here's geometric sequence. So here's the sequence, and now I'm looking at the partial sums. So the sequence is a list of numbers: 9/10, 9 over 100, 9 over 1,000, etc. That's the sequence. The partial sums are what you get when you add up the sequence. You see the difference between a sequence and the series. The series, you were adding them all up. Now, one thing I kind of want you to notice here is the recursive nature of these partial sums. S1 is A1. S2 is A1 plus A2. You follow? S3 is A1 plus A2 plus A3. You with me or not? You see what's happening here? S4 is A1 plus A2 plus A3 plus A4. Okay. So something that's worth noting is that S sub n is equal to S sub n minus 1 plus A sub n, or another way to think about it, which we'll talk about tomorrow. Whoops. You think of the nth term defined recursively as you add up the first n terms, subtract off the first n minus 1 term, that just leaves you with the nth term. Does that make sense or not? All right. So if you go through this process for this particular thing, you notice a pattern. The number on the top is exactly 1 less than the number on the bottom. And the number on the bottom, let's see, S5, this is 10 to the what? 1, 2, 3, 4, 5. So this is 10 to the 5th minus 1. This is 10 to the 4th minus 1 over 10 to the 4th, all the way down the line. And so we can get a formula for S sub n. And then as n goes to infinity, 1's going to stay 1. 1 over 10 to the n is going to go to 0. And so the limit is 1. So that essentially tells us, if I look at what this is, this is another proof that 0.9 repeating is actually equal to 1. Okay. So every decimal representation of a real number is an infinite series because it is an infinite sum of digits. So for example, like the square root of 2, (1.414) blah blah blah, you can think of that as 1 plus 4 over 10 plus 1 over 100 plus 4 over 1,000, etc. Every single real number is the sum of an infinite series. Okay? All right, so here's these definitions again. We started with these at the top of the hour. Here they are again recorded for you in your notes, so you have them. Once again, the sum is defined as the limit of the partial sums. If the limit of the partial sums exists, we say the series converges. Otherwise, we say the series diverges. It's the same language we've used for sequences. It's the same language we use for improper integrals because it's the same concept. Properties of convergent series. Since convergent series are defined in terms of limits of finite sums, the properties of limits and finite sums can carry over. They can work together to give us properties of convergent series. For example, the constant multiple rule. If you have a finite sum, if you have a constant multiplying every term, what can you do with that constant? You can factor it out. What rule is that? That's the distributive property. You're just reading it one way for so that's distributive property. Okay. Now, do limits respect constant multiples? If a limit exists, what can I do with the constant? Bring it out front. You follow or not, folks? Okay. So if you have a convergent series, if AK's converge and C is a constant, you can move that constant out front. What about addition and subtraction? Can you rearrange terms with addition and subtraction and regroup terms? What rules are being used there? What rule allows you to rearrange things and regroup things? The rearrange stuff is what rule? Commutative property, and then the grouping is the what rule? Associative. And the negative there, that's another distributive law if you have it. You follow? So finite sums work well doing this sort of thing. How do limits behave with addition and subtraction? Are they cool with that? And so that gives us this property. Okay. The key, though, is you have to have convergent series to use these properties. Just like when you use limit properties, you need to know the limits exist to use the limit properties. Like on the one on the take-home, which once again, yesterday, Adam was here. The internet died about 1:45, and then it just never really came back. So I started grading the Calc 1 stuff, couldn't get back to it. My plan for all day today is to just grade. So we'll see how far I get today. Hopefully you'll have all your scores in tonight. If not, by tomorrow night. All right, geometric series. So once again, what's the difference between a sequence and a series? A series is you're adding terms of a sequence. But the series itself is a limit of the sequence of partial sums. You follow? So a series is the limit of a sequence. It's the sequence of the partial sums. But when you think series, you think you're adding things up. Okay. Suppose I want to add up a geometric series. Okay. Well, let's take a look at the sort of the fringe cases. What if a is equal to 0? If you start at 0, then 0 times anything is what? So this is going to add up to what? 0. So the things we're going to be caring about here, we're going to look at a non-zero number. Okay? I suppose r could be 0. I suppose r could be 1. You follow? So these are some fringe cases we're going to be looking at here. All right, formulas for geometric series. All right, here, if r equals 1, then the formula for the nth partial sum, you're just adding a to itself n times. Does that make sense or not, folks? If r is not equal to 1, then here's your formula for Sn. All right. Now there's a couple different ways to get at this formula. Let's see why this works. So we're assuming that r is not 1, and we're assuming a isn't 0 because we just don't want to deal with it. But let's look at this. Let's look at S sub n. So you got to remember here that because of how the sequence is defined, right, that's our formula for the sequence. So because we're starting off with a and not ar to the first, if we add up n things, we're going to end up at n minus 1 on the exponent. Does everyone see why the n minus 1 on the exponent here is 1 less than the n? Does that make sense or not? It's because we don't have an r here. You with me? So I'm going to multiply then everything by r. So r times Sn is going to multiply all these things by r. I'll have an RA. Whoops. Put it the other way. AR. This would get bumped up to AR what? Squared. This would get bumped up to AR cubed. And then the term before this would be AR to the n minus 2. That would get bumped up to AR to the n minus 1. And then the AR to the n minus 1 would get bumped up to AR to the what? N. So now if I subtract these two things, look what happens. I get SN minus RSN. The A here. But what's going to happen to AR? I'm subtracting one of those off. You follow? AR squared. I'm doing what? You follow? Everything in here is going to do what? Cancel out except who's left over. You follow or not, folks? Okay. So now it's just a matter of factoring. I'm going to factor out the S sub n. Factor out the A. Oops. S sub n. A times 1 minus r to the n over 1 minus r. So that's the formula. So the term itself is 1 power less than that, but when you add them up, these things match. Okay, those exponents match. Okay? So that's where it comes from. It comes from a little algebraic manipulation. Now, using this, where did that formula go? We can talk about what happens if we try to take the limit of the partial sums. And this comes back to what we did yesterday when we looked at limits of things that look like r to the n. You follow? So we know what happens here from what we did yesterday. Do you remember what happens? What does r have to be to guarantee that limit's going to exist? It's got to be between -1 and 1. You follow? It's got to be between -1 and 1. If it's between 0 and 1, then it just goes to 0 on its own. If it's between -1 and 0, then it's just going to oscillate, but it's going to get closer to 0. We did the squeeze theorem on that. Okay? So this is going to be, once again, we're assuming that r isn't 1 here. This is going to equal, well, let's see. This will go to 0 then, and this will be equal to a over 1 minus r, provided r is between -1 and 1. Or a quicker way to write that is the absolute value of r is less than 1. So that's going to be a formula we're going to be using over and over again when it comes to geometric series. So we're going to write it on a new slide. Put a big star next to it. A plus AR plus AR squared plus ... equals A over 1 minus R. And this is valid exclusively for when the ratio in absolute value is less than 1. The way I like to remember this formula is that the A, think of that as the first term, over 1 minus the common ratio. And then the series diverges otherwise. Okay? Series diverges otherwise. So this is the formula you should know. You should just know it. Put it on a flashcard. All right, so let's practice these formulas. Suppose you collect 1 penny on April 1st, 2 pennies on April 2nd, 4 pennies on April 3rd, and so forth, doubling the amount of money you receive each day. How much money will you collect on April 5th, April 15th? What's the total money you'll have collected on those dates? What's the total amount of money you have collected by the end of April? Okay? So there's 2 questions here. How much you're getting on a certain day, and then how much you've collected so far up to that point. You with me or not? Okay, so let's write this down. You've got, on your first day, you've got $0.01. On the second day, you have $0.02. On the third day, $0.04, and so on. It tells you every day you're doing what? You're doubling, right? So this is an honest-to-goodness geometric sequence here. A sub k equals AR to the k minus 1. The A here is how much you started with, which in this case is what? 0.01. And what's the common ratio? How are we going from one to the next? We're always multiplying by 2. So 2 to the k minus 1. So that's our A sub k. So how much do we collect on April 5th? Just that day. Well, April 5th would be the 5th day of April, so I'd be looking at A sub 5, 0.01 times 2 to the 5 minus 1. Well, that's 2 to the 4th, which is what? 16 times 0.01. Okay. So on April 5th, on that day alone, I've collected 16 cents. You with me? Now, if I move along to April 15th, that'd be A sub 15. And that's a bigger number. It works out to be $163.84. You follow? Now that's how much I collected on just that day. That's not much. That's not the total I've collected in April. If we want the total collected as of April 15th, that's the partial sum. You follow? Because that's how much I got on the first day, plus the second day, plus the third day. That's how much I had on April 1st, plus how much I got April 3rd, all the way up to April 15th. So that would be S15. You follow? And I have a formula for S15. It's right here. So S15, A, once again, that's the first term. How much did I collect on my first day? A penny. 1 minus R, what's the common ratio? 2. N here is how much? How many days here is I'm looking at? 15 over 1 minus R, 1 minus 2. So you can see what will happen here. This will be a negative 1. So total collected on that day, that'd work out to be $327.67. So halfway through the month, if you're doing this scheme, you've raked in like $328. You follow? So what's the total amount you'll collect by the end of April? So if halfway through April you've got a little over $300, what would be your guess as to what you'll have at the end of April? Well, how many days does April have? April's got 30 days, right? So using my formula, look what's going on. I'm having 2 to the 30th power. You follow? That's a ridiculously huge number. I'm going to be multiplying it by 0.01, but still, right? It turns out you get, how much is that? 10 million bucks? You with me or not? So there's a, this is usually called the penny problem. This is an update of the rice problem. where in ancient China, someone beats the Chinese emperor at chess, and it says, okay, you can have anything you want in my kingdom. He goes, I'll take a grain of rice on the first square, and then 2 grains of rice on the second square, and then 4 grains of rice for the third square, for all 64 squares. And you can calculate how much rice that is. And it's beyond the production of rice in China for years. Okay, but that's the power of geometric growth. Okay. All right. Determine if the following series converge or diverge. If the series converges, find its sum. So once again, we have these formulas here for a geometric series. Geometric series, we're adding up. Okay. Geometric series, you could write them, if you write them starting at 0, they look like AR to the K. If you once again, you can shift the index, etc. But here's what's going to cue you in on if you've got a geometric series at your disposal. Look for where the K is. You follow? If the K is appearing only in the exponent, then there's a chance that you've got yourself a geometric series. You follow? Geometric series correspond to exponential functions. In exponential functions, the variable's in the exponent. So in geometric series, the variable's in the exponent. Okay? So looking here, if you're looking at where the K is, the K always seems to be up in that exponent. You follow? So what we can do is we can analyze this series. We can see if it's geometric. So I need to find R, look at the absolute value of R. If that's less than 1, it's going to converge to A over 1 minus R. Otherwise, it'll diverge. That's it. You follow? So let's take a look at this first series. Three times negative 2 to the K power over 5 to the K minus 1. So we suspect it's a geometric series because the K's are in the exponents. To actually prove it's geometric, we have to show that the ratio of adjacent terms is always the same number. So remember, R is A sub K plus 1 over A sub K. So our A sub K is our kth term. Oops. And then I need to get my A sub K plus 1. Now remember, this is just like function notation. So if I want to get an expression for A sub K plus 1, everywhere I see a K in the expression for A sub K, I'm going to replace it with the quantity what? K plus 1. So I'd have 3 times negative 2 to the K plus 1 power divided by 5 to the what? Kth power. Is everyone okay getting an expression for the A sub K? Now, more often than not, when you're looking at these series, for geometric series, you're going to have fractions involved. And so a little tip here. Remember, when you divide two numbers, that's the same as multiplying the first number by the reciprocal of the second. So let's start with A sub K plus 1. Times the reciprocal of AK. So I'm just going to flip this over. And if this really and truly is a geometric series, all of the k's should cancel out. So let's see what happens. Well, what happens to the 3's? Completely gone. Right? Let's look at negative 2's. I've got negative 2 to the k plus 1. I'm dividing by negative 2 to the k. So it's going to leave me with the negative 2 to the first in the numerator. Is everyone cool with that? Let's look at the 5's. I've got k factors of 5 in the denominator. I've got k minus 1 factors of 5 in the numerator. That's going to leave me with how many factors of 5 where? We all cool with that? So this proves we have a geometric series because when we take the ratio of the terms, we get a number. Okay. So now we check. We take the absolute value of that ratio, 2/5, and we need to check, is this less than 1? Yep. That means that we know this series converges. You follow? So that's how you would prove that this series converges. But what's nice about geometric series is not only can we show they converge, we can actually find out what they converge to, what they add up to. So the sum, k goes from 1 to infinity. Of 3 times negative 2 to the k over 5 to the k minus 1 is going to converge to a over 1 minus r. The first term over 1 minus the common ratio. So the common ratio r we determined. We needed that to prove it was geometric. That's negative 2/5. How do I get the first term? I go to my series. The series here, k starts at what? 1. So a is a1. I just plug that in. In the numerator, I get what? In the denominator, I get, you with me or not, folks? So now I just toss this in, negative 6 over 1 minus negative 2/5. I get negative 6 over, what do I have down here? 7/5. Do the fraction gymnastics. Negative 30/70ths, and you're done. Or negative 30/7ths, and you're done. See how this is working or not, folks? Look for k's and exponents only. Prove it's geometric. If the ratio in absolute value is less than 1, it converges. And now we know how to find out where it converges to. Any questions on this example? Let's look at number 2. Number 2 is ever so slightly different than number 1. What's the only difference here syntactically? We've got the sum going in the same place. We got a 3, we got a negative 2, we got a 5. The exponent here, instead of being k, is what? 3k. Let's take a look at this one. So once again, the kth term, negative 2 to the 3k, 5 to the k minus 1, a sub k plus 1. Everywhere we see a k, we're going to replace it with the quantity k plus 1. Quantity here, 3 times the quantity k plus 1 over 5 times the quantity k plus 1 minus 1. So what's going to be the exponent on that negative 2 now? It's what? What do you get? 3k plus 3. And what's the exponent on the 5? Okay. So, to prove it's geometric, I need to take the ratio of ak plus 1 over ak, or ak plus 1 times 1 over ak. So in this case, that's 3 times the negative 2 to the 3k plus 3 over 5 to the k times the reciprocal of ak. And now I go to simplify. So once again, what happens to the 3's? Gone. Let's look at the power on the 2 here. I've got negative 2 to the 3k plus 3 here. I'm dividing out negative 2 to the 3k. So how many factors of negative 2 am I going to be left with in the numerator? Three. I've got k factors of 5 down here. I've got k minus 1 factors of 5 up here. So I'm going to be left with how many factors of 5? There we go. I simplify this. What's r? Negative 8/5. So is the series geometric? Yep. Because if I take the ratio of successive terms, I get a number. Now, does this geometric series converge? Let's find out. The absolute value of r would be positive 8/5. Is that less than 1? Nope. It's bigger than 1, so that means that the series diverges. And that's all they wrote. You follow? So, you can spot a geometric series, but you need to prove it's geometric to use the theorem by looking at the ratio of those numbers. The nice thing is, if it converges, then you've got half your work done for finding out what it converges to. You follow? Let's take a look at number 3. It doesn't quite look like a geometric series. We've got this subtraction happening. But we know that we can separate numerators. And each of those individually look geometric. You follow? So I can look at those two things individually. If they both converge, I can use properties of convergent sums to write this as the difference of those two convergent sums. So we'll look at each of these individually. So on the first series, the terms are 4 to the k over 3 to the 2k. So what would be an expression for a sub k plus 1? It would be 4 to the what? K plus 1 over 3 to the what? 2k plus 2. Good. So if I go to calculate r, a sub k plus 1 times 1 over a sub k. How many factors of 4 am I going to have, and where are they going to be? One factor of 4 in the numerator. How many factors of 3, and where are they going to be? 2 in the denominator. That's a 4/9. The absolute value of r is 4/9. Is that less than 1? That means that this series converges. Do you follow or not, folks? So this one is good to go. Now I have to look at the second one to see if that also converges. Any questions on the first one, the analysis there? You getting the hang of this or not, folks? Okay. Let's look at the second one. Once again, k goes from 2 to infinity, 2 to the k minus 1 over 3 to the 2k. So my a sub k, 2 to the k minus 1 over 3 to the 2k. What's an expression for a sub k plus 1? Perfect. We all good with that? Now we'll check to see if it's geometric. I need a sub k plus 1 times 1 over a sub k. I'd have 2 to the k over 3 to the 2k plus 2 times the reciprocal 3 to the 2k over 2 to the k minus 1. And so when the dust settles, how many factors of 2 do I have and where do I have them? I've got k factors of 2. I'm dividing out k minus 1 factors of 2, so I'm left with how many factors of 2? One factor of 2 there in the numerator. What about this? How many factors of 2 am I left? 2 factors of 3 in the denominator, so this ratio is 2/9. Is that less than 1? That means it converges. So since each individual piece converges, I can use properties of convergent sums. So the original sum that they started me with, the sum k goes from 2 to infinity. I'll just use my spare handout over here. Uh, 4 to the k minus 2 to the k minus 1 over 3 to the 2k. Because of properties of convergent sums, that's the sum k goes from 2 to infinity 4 to the k over 3 to the 2k minus the sum k goes from 2 to infinity 2 to the k minus 1 over 3 to the 2k. And the sum k goes from 2 to infinity of 4 to the k over 3 to the 2k. Once again, that's going to be the first term over 1 minus the ratio. How am I going to find the first term here? Well, where does the k start? 2. So I'd plug 2 into that. I would get 4 to the 2 over 3 to the what? 4th? 1 minus the ratio. We determined the ratio as part of our analysis. That was 4/9. So I would have a 16 over 81 divided by 5/9. So if I invert and multiply, what do I get? The 9 will cancel. 16 over what when this is all done? 45, is that right? We flip things around, does that look good? Does that track? Let's look at the second one. K goes from 2 to infinity. 2 to the k minus 1 over 3 to the 2k. Once again, this converges to the first term over 1 minus the common ratio. The first term here, once again, k starts at 2. So 2 to the 2 minus 1, it's going to be 2 to the first over 3 to the fourth again. Divided by 1 minus the common ratio for this series was what? What did I lose it? Where did it go? 2/9? So this would be 2 over 81 divided by 7/9. So you flip the thing around. 9 times 7 is 63. Excuse me. The final answer would be 16/45 minus 2 over 63, whatever that works out to be. Fine. So you can use properties of convergent sums to rewrite things as long as each individual piece converges. At the end of the day, those properties of convergent sums are limit properties. And you can only use limit properties when all the constituent limits exist to begin with. Any questions on the sort of techniques you saw there in example 3? All right, let's take a look at example 4. Now, what's different about this series than the series we've been working with? Well, the counter here is k. That's the index of the summation. But we have a what in there? We got an x. Okay? Determine all values x for which the series converges. What does it converge to? Check graphically. So something cool happens here. So let's look at this one. First off, let's talk about what happens when we go to write this out. When we go to write this out, we have an x up here. Now notice the first k you plug in is k equals what? 0. So this would be an x to the 0 over 2 to the 0 plus 1. And then an x to the first over 2 to the 1 plus 1. Plus an x squared over 2 to the 2 plus 1, and so on. Okay? Now, in this particular context, in Chapter 10 and Chapter 11, when you get like for example, if we wanted to plug in like x equals 0 here, because this is a function of x, right? This is technically what's called a power series, and we'll be studying these in Chapter 11. But if I were to plug in x equals 0, you might say, well, wait a minute, that's a 0 to the 0 there. Zero to the 0, typically, you've seen it as an indeterminate form where there's limits involved. You follow? In this particular case, when this happens, it's not like we're taking a limit as x is going to 0. We're plugging 0 in. We're going to define this, in this particular case, to always be 1. You follow? So regardless of what x is, so when you see that 0 power there, whoops, this is defined to be a 1 all the time. So that would be a 1/2 plus x over 4 plus x cubed over, or x squared over 8, and so on. You follow or not, folks? Okay. All right. So that's just a legal disclaimer. I've got it on the handout as well. So it asks, for what values of x does this series converge? So if you look at this series, and I look for where the k is always where, folks? In the exponent. That means that even though there's an exit there, which is its own thing, this is a geometric series. We can determine that by looking at the common ratio. So a sub k is x to the k power over 2 to the k plus 1 power. What's a sub k plus 1? Everywhere you see a k, you're going to plug in k plus 1. So this would be x to the what power? K plus 1 over 2 to the what power? K plus 2. And so if I go to look at my ratio here, R equals a sub k plus 1 times 1 over a sub k. I've got an x to the k plus 1 over 2 to the k plus 1 times the reciprocal, over x2k plus 2 times the reciprocal to the k plus 1 over x to the k. And once again, just like we're not worried about 0 to the 0, we're not worried about 0 over 0 either. Okay, folks? What's going to happen when I simplify this? How many factors of x do I have left after I do this calculation? And where is it? And how many factors of 2 do I have left over when I do this calculation? And where is it? Is everyone cool with that? This proves it's a geometric sequence because the ratio doesn't depend upon who? K, which is the counter. You follow? So for this to converge, I need the absolute value of r to be less than 1. So I need the absolute value of x minus 2 to be less than what? 1. Now I got to go do some algebra. But think about absolute value. The absolute value of something is its distance from 0. Right? You might remember this when we did epsilon delta stuff in Calc 1. So if the absolute value of something is less than 1, then that means that it's within 1 units of 0. You follow or not, folks? So that means I can rewrite this as x over 2 is trapped between negative 1 and 1. And to get rid of that, dividing by 2, I can multiply through by what? 2. And since 2 is a positive number, it doesn't screw up the inequalities. We all cool with this? So, as long as x is between negative 2 and 2, x over 2 is between negative 1 and 1, which means that this series will converge. So if I think of this series as being a way to define a function, then really, when I'm asking where does this series converge, I'm really asking for the domain of that function. Make sense or not? Okay. Now here's where it gets pretty cool. Because now it says, what does it converge to? So, as long as x is between negative 2 and 2, once again, it's the first term over 1 minus the common ratio. And how do I get the first term? I look at where the k starts. K in this case starts at 0. And what did we all agree x to the 0 is going to be, regardless of what x is? 1 over, plug 0 into this. So I get a 1/2 there in the numerator, over 1 minus the ratio. The ratio we worked out to be x over 2. So if I go through my gymnastics here, multiply everything by 2, I get a 1 over 2 minus x for x between -2 and 2. So if you write this out longhand, what this says is that 1/2 plus x over 4 plus x squared over 8 plus s cubed over 16 plus ... That's going to somehow add up to 1 over 2 minus x. Right? So the thing on the left just looks like a polynomial that keeps going forever. You follow? The thing on the right is a rational function. We're adding up. So let's look at what this is on Desmos here, and then that'll be it for us today. So how do I dial this in on Desmos? Well, here's what we do. We type in the f of x, and we write sum for sum. Boom, there's our sum. Now we have our counters as being k, so I'm going to just arrow over and change that to k, and I'm going to go to 0, and we're not going to go to infinity, we're just going to go to n. So what I'm going to be graphing are these partial sums. Okay, and what goes in there? I had x to the k power over 2 to the what? K plus 1, and you got to use parentheses or else it'll drop it out. Now we're going to add a slider for n. We're going to start n at 0. We're going to go to, I don't know, 20 with a step of 1. All right. Okay. Now watch what happens. So n, remember, we're graphing the partial sums. The partial sums of this function, s1 would be the function 1/2. s2 would be 1/2 plus x over 4. s3 would be 1/2 plus x over 4 plus x squared over 8. You with me or not, folks? You follow? When you graph these functions, what do I expect? What's the graph of y equals 1/2 going to look like? Horizontal line. What's the graph of 1/2 plus x over 4 going to look like? What's the graph of this going to look like? You with me or not? So these partial sums are polynomial functions, and yet somehow they're going to add up to this rational function. So let's watch what happens here. You with me or not, folks? Now, what's this supposed to add up to? It's supposed to add up to, at least between -2 and 2, 1 over 2 minus x. Was that right? Okay, so that's what it's supposed to add up to. You follow? Let's check it out. Do you see it doing the work or not, folks? So that's convergence of functions. These polynomials are turning into that function. Isn't that wild? Yeah, it's pretty wild. Telescoping series. Which the integral analog of these are partial fraction integrals. So we'll get to use our partial fraction stuff today. We'll get to use Heaviside method again today to see how this works. So let's start off with the example we have there on the handout, which I need. So we're looking at the sum, k goes from 1 to infinity of 1 over k squared plus 3k plus 2. Now, it's not a geometric series because those k's aren't in the what? They're not in the exponent, right? So we don't have any hope it's a geometric series. So what we can do is we can start writing out the partial sums. And that's what we get for the partial sums. We get a sixth, a quarter, 3/10, a third. And we could keep going. And there doesn't seem to be a rhyme or reason to it. All right? That being said, if we remember back to yesterday, one of the things we talked about is how the infinite series can be thought of as a discrete integral. So sometimes solving these things, we can think same kinds of strategies. So if we were trying to figure out what's going on with this integral, you might recognize this from the first week as being something we can totally do partial fractions on, because the numerator is easily factorable as a product of linear factors, which means we can break it up. So that's what we're going to do. We're going to try partial fractions on this thing. So the first thing we do is factor. How does that denominator factor? So k squared plus 3k plus 2. So what do I get out of that?
K plus 2 and k plus 1.
Perfect. Now what's nice about these is they're distinct linear factors. So once again, partial fractions is where we're trying to reverse the process of getting a common denominator. So I look at what little denominators would factor, pun intended, into this. Well, I've got a k plus 2 factor and a what? K plus 1 factor. And so we're going to have some constant above each of those. And now we can go ahead and use that Heaviside method if we want. Use the Heaviside method, multiply both sides, whatever you want to do. So what we do is we look at this factor here, and what value of k is going to make this 0? -2. I come over here. I'm going to cover up that factor. I'm going to plug k equal -2 into what's left over. A equals 1 over -2 plus 1. It's going to give me A. I come over here. I set this factor equal to 0. What do I get for k? -1. I'm going to come over here, cover up this factor, plug -1 into what's left over, so I get b equals 1. Okay. Alternatively, you could multiply both sides by the denominator and then cheese by putting in -2 and -1. That amounts to the same thing. Or you could multiply both sides by the denominator, equate powers of k. You're going to get to the same place. All right. So how does this help us? So instead of trying to analyze the series with the terms written this way, let's look to see what happens if we look at the series with the terms written this way. So I've got let's see, b is the positive one, so I'll put that first. A 1 over k plus 1, and then a has the -1, minus a 1 over k plus 2. Okay, there it is. Okay. Now, here's what we can't do. We can't do this. We did one like this yesterday where we could split it up. Do you remember under what circumstances you can split the series up like that? What do we have to know about in the individual series? They have to both what? Yeah, they got to both converge. Do we know if these things converge individually? In fact, spoiler alert, they don't. So this would be a big no-no. Right? Essentially what's happening here is we're actually getting an infinity minus infinity, which we'll talk about. Actually, well, we'll sort of know about this at the end of this week. The point of doing this is hopefully what this will do for us is it'll help us figure out what the partial sums look like. All right. So let's do that. So I'm just going to recopy this. And once again, partial fractions, it's like we're unsimplifying, right? We had a one fraction, we're turning it into two. Why? Because we hope by turning it into two and unsimplifying, it's going to make our calculus easier. So let's go through and let's look at S1. Remember, S1 is the sum of the first term. So the first term starts when k equals 1. So that'd be a 1/2 minus a 1/3. That would be S1. Now we don't want to simplify this because we would just get right back to the simplified version of the partial sum that doesn't give us any pattern. You follow? The whole point of doing the partial fractions was to unsimplify to see what we get. Now for S2, well, we're going to add up the first two terms. So once again, we've got the S1 already. That's the first term. Now we're going to add on the second term when k is 2. And look what happens. Those things are going to do what? Totally drop out. So once again, we don't want to get common denominators because the whole point of the partial fractions was to undo that. You follow? Let's look at S3. S3 is the sum of the first three terms. But remember, what we talked about yesterday, I have the sum of the first two terms already. We're just going to tack on the third term. And look what happens here. S4. I'm already going to get S3. The sum of the first three terms is going to be 1/2 minus 1/5. I just have to add on the fourth term. 1/5 minus 1/6. Those drop out. So let's check it out. Are you seeing a pattern evolve now? What would be your guess for S5? What's your guess going to be? 1/2 minus 1/7. Does that make sense or not? Okay. Now, if you wanted to actually formally prove this, you'd have to use something called the principle of mathematical induction, which back in the old days they used to teach that like in pre-calc. It's in our pre-calculus book. It doesn't get taught anymore. Grandpa can teach you that today. PMI. It'd be a good bonding moment. The principle of mathematical induction. But for us, we're just going to recognize the pattern. S sub n, what would the pattern be? Well, it always starts off with what? 1/2 minus 1/, and then how is this number related to this number as we go down the line here? How did you know that S5 would end up with the 7 there? What did you do with that 5? Added 2. So what's going to go here? Make sense or not? Okay. So now we can take the limit as n runs off to infinity of S sub n. That's the limit as n runs off to infinity of 1/2 minus 1/n plus 2. And once again, now we're back. We're looking at the limit of a sequence. The sequence here being the sequence of partial sums. As n runs off to infinity, what happens to the half? What happens to the 1/n plus 2? So our final answer is 1/2. And so we can say that the sum k goes from 1 to infinity of 1/k squared plus 3k plus 2 converges because the limit exists. But not only that, it converges to 1/2. So that means as you take successive partial sums, they should be adding up closer and closer to 2. And I'll give you a minute to copy stuff down, and we'll fire up Desmos to check that. So once again, to get the sum in Desmos, to get the sigma, you just type in the word sum. And we're using the counter k here. So we're going to go k, we went from 1, and we're going to go to n for our partial sums. 1 over k squared plus 3k plus 2. And for our slider n, we'll have n, see k starts at 1, so n should start at 1 and go to, I don't know, 100 or something, or 1,000 with the step of 1. And then we can see here, that's our partial sum. So the first one was whatever, a sixth or whatever. And then here we go. According to our analysis, these should get closer and closer to what number? A half. Do you see that happening? I mean, they're getting like 0.49 something. You follow? If we called this thing f of n, and we could plug in like f of a billion or something. Is that going to do this? Will it not work for you? Oh my goodness. Desmos didn't like that. Oh, there we go. So we can just do this now. Just start plugging in ridiculous numbers. Eventually, look what's going to happen. Because sometimes it'll round to 0.5, sometimes it all depends on the floating point round-off error here. If you go far enough, sometimes it breaks. I think it broke. Look, it's stuck. Anyway, okay. We only use technology to confirm, to guess, right? We proved it actually goes to a half, right there. Okay, example 5, video for this. Once again, these are partial fractions. You get in there, do your partial fractions, observe the pattern. Okay. These are called, in the business, these are called telescoping series. All right. Can anyone think why? It's these old-timey telescopes that used to collapse. So you have these old-timey telescopes. They would, you take it out of your pocket, you would extend it, and then you collapse them. All right, that's why. Because what happens is, if you take the time to write out the partial sums, you see how all these terms in between collapse. You follow? So you've seen a telescoping. If you had a proof of the fundamental theorem of calculus, you've seen this kind of thing happen before when you chop up the partitions. But anyhow, that's why it's called telescoping, if you wanted to know. All right, and then there's homework there from the book. Now, as an appendix, of course, something a little extra here. We talked about last week how the compound interest formula, when you compound things n times a year, is a geometric sequence. And then on the take-home, you went in and you showed that the limit of the discrete compounding turns into the PERT formula. So there's a thing called an annuity. And a lot of retirement funds are like this, but also mortgages are like this, sort of in reverse, where instead of just putting in like a chunk of money and letting it sit, you put in a little bit of money each month. So it's like, okay, every month you're going to put in $25 to this account. So what happens is you put that money in, and then for the month that it's in there, it's going to accrue interest. And then on the next month, you've got what you had before. Now you're going to add another $25, and it's going to accrue it. You see what I'm saying? So we're adding it. Basically, anything that involves payments and compound interest is an annuity. If you take a loan out to buy a car, that's like the bank having an annuity with you. You follow? So feel free to read through this. Once again, this is out of the pre-calculus book. We go through here and derive the formula for an annuity. And you can kind of see right here, it ends up being we get a geometric, we get a we get the partial sum of a geometric sequence, which we can then go through and get this formula. Right? So this is like the payment calculator type thing you would have. And then there's an example. So there you go. So what good is this? Well, there you go. Anytime you take out a loan to do anything, it's essentially an annuity calculation.